All right, so this is the Game Engine Development Workshop Series. We're going to be hosting it every Wednesday and Saturday from 4 p.m. to 5:30 p.m. Central Time, UTD time. I'd like to make the distinction. I think in some of the advertising it was the Game Development Workshop Series, which is not exactly the same thing. We're going to be focusing on more of the technical aspects of game programming rather than game design. But if you're more interested in game design, I still think this could be valuable for you if you were sort of suckered in here by some of the poor wording. All right. So first of all, what is a game engine? Well, I have the Wikipedia definition here, which is very trustworthy. It's just the core software necessary for games to run. So everything that handles graphics, audio, input, game logic. Basically, it's code that is, I don't want to say boilerplate, because as we'll see, there are infinite many different ways to do this stuff. So it's not quite boilerplate, but it is always necessary to some degree. And so there are popular commercial game engines. Unity and Unreal are the biggest. I'm sure many of you have heard of those or used those. And those have like a this sort of back end written in C++ that handles all the graphics, audio input, and then the user interface is like this sort of massively complex map asset editor combo with like C# scripting thrown in there. So that's sort of like I would say the end game of any sort of game engines. It has all this necessary software for games to run, and then all these cool tools as well that they can actually sell as like a software package. So let's quickly go through some of the survey results. By the way, thanks for filling those out because those were very helpful in figuring out what to actually do for this. So in terms of game engine experience, 31% have either used a game engine or tried to make one, which is pretty good. I'd say that's about what I was expecting, 1 in 3 people. 38% think about how games work, but they've never really used an engine. That is also good. Like, obviously, it's better to have some experience using game engines, but as long as you think about this stuff, like you're just sort of mentally prepared, already in that headspace of like, trying to figure out what's necessary for a game and how existing games work. 31% don't know what a game engine is, which is also totally fine. Once again, this series will be entirely from the ground up. All I'm really assuming is that you have like basic to intermediate knowledge of C++, but all of the like game logic, graphics, everything we're going to be doing in these workshops. So if you have zero experience, don't worry about it. Yeah. So interest though, this was the big one in like determining what we're actually going to be doing. 84% are into core utilities, 75% are into graphics, which is perfect. Like those are the two main components of any game engine. So I like if those weren't as popular, I'm not really sure what we would have done because obviously core utilities you need your game to be able to do stuff, and graphics, if you can't draw anything to the screen, it's going to be a pretty boring game. So I was glad to see those results. And then the sort of like end goal of this series is going to be a scripting language. 79% wanted a scripting language, which I think is really cool. That is one of my interests. Sort of going back to what I was talking about here, how they have like all these asset and map editors, just like these general development tools. I'm really into that. I like making stuff that helps me make stuff, I guess. And I think a scripting language is sort of like the ultimate version of that. It's like your own programming language. But yeah, we'll talk about that in a bit more. C++ stuff. So there were a couple questions about like which of the following do you have experience with, yada yada yada. Most of you were pretty comfortable with what we'll be doing, which was fine. Like there was nothing too surprising. Like I don't think anyone said like, oh, I have no experience with C++, which was good. But what did surprise me was that 70% have no experience with the language outside of classes. So this is not terrible. I think what this signals to me though is that like you have learned this stuff. because obviously it's required at UTD as CS 2336 or 37, I think. And so you probably have learned a fair amount of it, but if you've never used it outside of the class, in my experience, I generally like forget stuff as soon as I stop using it. So you might have to play a little bit of catch up at the beginning, but that's fine. Like I said, this is going to be sort of the pace of this is going to be dictated by the people who show up to these workshops. So as long as you're here, you're participating, I don't think you'll have trouble like massively falling behind or anything like that. In relation to OpenGL, which I'll talk a lot more about in a minute, 51% had never heard of it, which is fine. Like, again, from the ground up. 39% have heard of it, which is good. Similar to what I was saying about how 31%, or wait, what was it? 38% think about how games work. Sort of the same thing there. And a small number of people have actually used OpenGL, which is good because I don't want to be covering stuff that a bunch of people already know. So I was pleased to see that. So now let's talk about what we'll actually be using for our project. As you already know, assuming you've done the required setup for these workshops, our language of choice is C++. This is basically the industry standard for any game development. It's low level enough that it runs really fast. Some people, I think I saw someone saying that like C is lower level, so it's faster. I don't think that's really the case. I'm sure you can find edge cases where the C++ compiler introduces some like unnecessary intricacies that the C compiler won't. But I don't know. When you start talking about that, it's just like irrelevant. So C is a lower level language, certainly than C++. It doesn't have any classes or anything like that. But C++ is a superset of C, and this means that all of the low level stuff that C can do, C++ can do as well. And sort of as a tangent to that, like C is faster than C++, C++ has this really nice template system, which we'll be making somewhat extensive use of, and I'll talk about like how it all works. But that can actually lead to faster code than code written or compiled with the C compiler. As I said, for graphics, we will be using OpenGL, which is the Open Graphics library. This is a bit, I don't want to say antiquated because it is still used, but it was sort of the first standardized graphics API. Came into popularity in the late 1990s. The guys at id Software, John Carmack, did a lot of that if you're like into the game industry stuff. And what it is basically is just it's an open graphics library. It is open source. People have built like stuff for every imaginable system that will let you use it on those systems. You probably noticed, or maybe you didn't, I don't know, if you looked at both the like Mac and Windows setup, you may have noticed that we had to use some different files for both of those, just simply because they are different operating systems. But one of the advantages of it being open source and also so used so widely for such a long period of time is that those things already exist. We just have to search for them, find them, and then use them. So one thing that I attempted to do while this was about a year ago, I think, I was starting to write like my first iteration of a real game engine in C++. And one thing I tried to do was write my own rendering API. But there are two very frustrating challenges that there isn't really a simple solution to. First of all, it would be different for Mac and Windows users. As I just said, you need different files to run the same thing on different systems. But the main problem I was running into was that it was a software renderer. So a lot of you have probably heard of GPUs, graphics processing units. If you haven't, don't worry. We'll talk about all of this once we start, right before we start doing all the graphics stuff. I'll sort of explain a little bit about the hardware and how it's important. But basically, a GPU is just either this separate component of many modern PCs, or in some cases, it's integrated onto the CPU. But it like massively improves graphics performance by parallelizing everything. So it's that sort of SIMD architecture that you've probably heard of. And So basically, you're either stuck with software, which is, CPU single pipeline, very slow, or if you want to write your own, you need to use these GPU APIs anyway. So my point here is that there's no real way to write something totally from scratch. At a certain point, you have to choose like a baseline of like saying, okay, this is software that I'm comfortable saying. There's no point in me rewriting it. That I don't really have much to learn from there, so I'm just going to use it. And for us, OpenGL is that. So what we'll be doing, well, again, from scratch, little asterisk there, with the exception of OpenGL, we will be writing a game engine. So we'll start with a simple math library. This will have some common functions, a couple useful classes. Generally, it'll be very small. It's really more of a C++ warm-up. That's more of the purpose of us writing it. So like for you 70% who haven't really used C++ outside of a class, this lecture, probably the next one, depending on our speed, I don't expect the math library part to take that long, but these should be sort of reintroducing you to C++, syntax and concepts, all that stuff, just to sort of ease you into it. And another reason is that, and we'll get into this once we start programming a bit more, it's important to wrap functionality early on, just sort of compartmentalize your program. Like for example, we could use the standard libraries math functions for like sine, cosine, all of that stuff. But if we want to change this functionality for some reason later on, if we want to add to it, I don't know what this would be. Again, it's a dumb example. But if we wanted to do that, it would be very difficult, right? If we've just used standard sine all across our program, we'd have to find all of them, replace all of them with the new thing. But if we just go ahead and wrap it from the beginning, then we only need to change it in one place. So it can help cut down on development time. And it's also just nice to know like which functions you're actually using. And again, I'll explain more a bit about that in a minute. So after this warm-up sort of math library section, we will dive into OpenGL. So I think I'm going to prepare like another PowerPoint just about the basics of graphics programming, graphics hardware. I'm by no means an expert, but I can sort of give people a crash course in like what's going on. But at first, we're just going to write a bunch of ugly OpenGL code just all in one file, and that way, like, I think the way I learn best is by knowing what the end goal of something is. And so the idea behind this is that we'll just sort of flesh out this ugly skeleton program, like the bare minimum to get stuff drawing to the screen. And then once we've done that, once you've been able to see the end result, then we'll start making it pretty and actually, like abstracting things out into classes and stuff. So then we will condense what I'm saying, compartmentalize that into a graphics library. We're only going to do 2D stuff. That's all we have time for. I'm sure you could extend it to handle 3D stuff. OpenGL doesn't really care that much. Like there's no mode saying, oh, I'm going to run this in 2D only or 3D only. That's not how it works. It just, you pass it a bunch of vertices and tell it what to do with them. So you could probably make this do 3D stuff if you wanted to, without too much hassle. And then finally, we will wrap our graphics library in an engine library, which may seem kind of dumb, but again, we'll talk about that when we get there. So of course, once we've got all this math and graphics stuff set up, we need to actually be able to do something with it. So that's the next part, is like the engine component of everything, which is just going to glue all this together and make it so that we can actually start designing like a playable game. So stuff like map data, which we'll do a little bit about. That was not very highly requested in the survey, so I've sort of glossed over that a bit. We're just doing like a simple, very simple like text file representation of map data. Dynamic objects, stuff that move around the screen, like the player, enemies for the player to shoot. Lighting stuff, collision handling, and of course our end goal of scripting. That's all going to be part of the engine component of the engine like wrapper library, combining all the previous stuff. Yeah, so a bit more about the scripting language. It was by far the most requested, like advanced topic. Unfortunately, we do have to do it last, just because in order to script stuff, you have to have stuff in your engine to script. And I guess at this point I should ask, is everyone, because maybe not everyone picked this option, but is everyone familiar with what a scripting language is? You can, like, you don't have to be on mute, by the way. I don't really care, as long as you're not making a ton of noise. Okay, is anyone familiar with what a scripting language is?
Sort of.
Okay, a couple people. Okay, I'll
Yeah.
talk a bit about that then. So, scripting language is a very broad topic, and I think I mentioned this a little bit when I was talking about those commercial game engines, Unreal Engine and Unity. Their scripting language is C#, which is essentially the only interface between the engine, like backend of Unity or Unreal, and the programmer. That's the only way they have to access the actual code that's being run. The rest of it is just through this like UI interface. And C# is like a fully blown programming language in itself, obviously. So we're not going to do anything that complicated. But basically, the point of a scripting language is it's some type of interface between the engine and the programmer that is simpler and faster to use than just hard coding stuff into the engine itself, right? So say like you want to write a script to control your player. Then within your scripting language, you could say, okay, I'm going to like get the state of these various keys on the keyboard, the arrow keys or WASD, whatever. And depending on that state, I will set my player's velocity, something like that. And that is a lot cleaner to do from like a user standpoint than going into the code of the engine and creating like a new class called player, which has this sort of keyboard dependent velocity control hard coded in, and you have to like hook it into the update loop, all this crazy stuff. So basically the scripting language is just it's a tool for the programmer that makes it a lot easier to make games, and that's sort of the goal of writing your own game engine at all, right? It's like, well, you could use Unity or Unreal, but those are huge suites of software, and they have all these different things, and when stuff gets that big and that complex, you inevitably you lose efficiency, and you also lose people's interest rather quickly, I think. Like, I've never really been interested in using one of those just because I think it would be cooler to have a much smaller subset of their functionality, but know what's actually happening. And that's the reason we're writing an engine. And a scripting language will just sort of expedite that even further. So the cool thing about our scripting language is I'm sort of leaving the design of it up to you. What that actually means, we'll talk a bit more about when we get there near the end, because obviously, like, it's going to have to be useful to some degree, right? So we can't just write a bunch of nonsense. And I also have some ideas of my own that we can sort of incorporate if you're interested in those. Okay, so one of the survey questions was like, would you be okay with doing some self-guided PowerPoint stuff in between workshops? At this point, I don't think that'll be necessary, but depending on how fast we go in these lectures, that might change. But there is one bit of, I guess, homework that everyone should do every week, which is write comments. So this is a very important skill, and in my experience is like basically non-existent. I've worked as a software developer for 2 different companies. They've both had fairly large code bases, and almost none of their code is commented. That caused me a lot of hassle, and I sort of wasted a lot of time trying to decipher this stuff, and in turn that loses the company money, right? So the goal is, when you're writing software, is to allow people to read your comments instead of reading your code, because one of those is very easy and the other is notoriously difficult. Another thing about that is it will increase your learning speed a lot, especially if you are newer to C++ in general. Just going back and sort of deciphering this sometimes complex, like weird syntax will really help you out. And I think in situations like this where like all of this material is sort of been curated and condensed in a way that it's available to you in this neat little package, you want to get as much out of it as you can. And like I'll be transparent here. You probably already know this, but all this stuff I just learned online, right? Like you could go out and find all of the information I have about game engine stuff and do exactly what I've been able to do. The difference is that it's taken me a matter of years, right? And so I'm trying to impart to you all the experience I've gained over those years in this like 2 or 3 month long workshop. And obviously that's impossible, but I think writing comments will really help you get as much out of that as possible. And I would estimate, although somewhat arbitrarily, I don't know how you could really measure this, that just going back and explaining all the code in English sentences, I think it'll double like how fast you learn this stuff and also how deeply you understand it. Because it's one thing to like, even though these workshops are going to be twice a week, which is like frequent enough that you probably won't forget too much in between workshops. Just going back, like once every couple of days and writing some comments will really help cement this stuff in your brain, because everyone has other stuff going on, obviously, and it's easy to lose track of this, even just being away from it for 3 days. So I strongly encourage you to write comments. Some last things to remember. Number one is like the way we end up doing things due to time constraints and also just a lack of knowledge on my part. I can pretty much guarantee that no code we write, no system we design will be like an optimal solution to anything. But what I can guarantee is that all the stuff we're writing, all the stuff we're designing, it will be fast and it will be functional. And I think those are the two most important things. There are also, as I said before, infinitely many ways to design all of this stuff. And so if you have any alternative ideas that for how to do something that we're doing at the moment, and you want to bring those up, that is very good. I think like having discussions about this stuff is interesting, and like comparing and contrasting the different trade-offs through different approaches. I'll try my best to mention any sort of alternative approaches whenever we're doing something. But yeah, I strongly encourage you all to do the same thing. Also question everything. Like I said already, everything is going to be suboptimal to some degree. But also I've probably made a bunch of dumb, stupid, simple mistakes. Either in terms of like writing inefficient code or just like, I don't know, not explaining stuff correctly. So if you notice any of those, just point them out. Again, feel free to just go off mute anytime and like ask a question. I would love that. And the last thing is ask for illustrations. I myself am much more of a visual learner, and so I don't get much from like just hearing people lecture. And even though I'm going to be sharing my screen the whole time and you'll see the code I'm writing, that's not really visual. Like I think diagrams are more what I'm talking about. And once again, I'll try my best to include those wherever I think they're applicable. I'll show off my MS Paint skills. They're very good. But yeah, so like if you are struggling to understand something and you think a diagram would help, just ask about it and I'll throw one up in 30 seconds and it'll be fine. But yeah, okay, so that's all I had for like the intro. I guess before we get started, I want to ask, are there any questions about this stuff? Like, do you feel like you all know what the goal of the series is, how we're going to get there, everything we're using, and how it's going to work?
Clear to me.
All right. Okay. And secondly, I think I already mentioned this, but it is important. If you have not done the like basic setup, you're going to have to go back and watch the video because we are not covering that today. That was like mandatory for you to do before this because it's just there's no point. I can explain it in the setup document. There's no conceptual stuff to go over. It's just following steps. So everyone should have this like setup. Obviously, if you're on Mac, it'll look a bit different. But this is I'm going to be doing all this on Visual Studio, but I have verified that it works on Mac as well. So yeah, everyone just load up whatever project you like followed the instructions on. And the first thing we're going to do is get rid of all of this code. Just to sort of reiterate, I guess make sure that everything's working. Nothing should have changed, obviously, since you did the setup, but you should just be getting this blue screen with nothing on it. It says window name here. You can drag it around and not much else. So just close that. And yeah, we're not going to be doing any of this. This is all OpenGL stuff, which, as I said, we will be getting to probably in about a week's time, depending on how quickly we do all the math stuff. And that is what we're going to do right now. So I'm going to create a new folder. I'm going to add a new folder. I'll call this math. I'm going to create 2 new files, header files, all.h, which is just going to be like the sort of overall include file, and then core.h, which is where we'll have all of our functions and stuff. Oh, and another thing I'd point out is I think I talk really fast sometimes, and I might just like blaze through a lot of this stuff, especially if you haven't used Visual Studio before or Xcode before. So if at any point I'm going too quickly, typing too quickly, or like moving a bunch of stuff around and you don't know what's happening, just stop me. Like, don't let it get out of hand, because then we'll like really have a problem. But yeah, don't be afraid to tell me to slow down or anything. Okay, so in our all.h, again, this is just going to be sort of the general include file. So we'll go ahead and include core.h. And then in our pch.h, our precompiled header, I'm going to go ahead and include math, where is it? Math slash all.h. Math slash all.h. And you might have to do this like whole relative path thing where you have the 2 periods, which just means like go up a directory. If you want to avoid that, something I often do that for whatever reason I just forgot to include in the setup document, even though we changed this directly, is in the C++ and general settings, in the additional include directories, you could just go ahead and whack on solution dir right there. One sec, someone has an error. Okay, I'll get to that in a second. But if you just go and add this solution dir, we already have source and dependency slash include, so we can include all those without any folder names. But doing this will allow us to just have math slash all.h, and you can see it'll like give you the whatever that's called, like the IntelliSense, whatever. Someone says you have an error with GLFW window hint. Okay, you might have something like configured incorrectly. We're not going to be doing anything with that today though, so don't worry about it for now. All I'll ask is that you contact me after this session ends today, and I'll try and help you out with it. But for now, you should be fine because we're not using any of that. Okay, so now we'll get to work on the actual core stuff. This is going to be pretty simple. Like I said, there's not really, like, it's just to get you used to writing C++ again. So it's going to be easygoing, and some of it is trivial. So just know that I'm aware of that, and the whole thing will not be like this for sure. Someone asks, is the math folder supposed to be inside the deps folder? No, I mean, you can put it wherever you want, but I'm organizing it so that I have dependencies, math, and source as separate, I guess, like top level folders. Also, don't be afraid if you have mics, just ask the question. You don't have to type it. Don't worry about interrupting or anything. Okay, so let's set up all of our includes for our core file. We're going to need C math, which has a bunch of basic math functions that will essentially just be wrapping directly. We're going to include int types.h. If you're unfamiliar with C++ or just out of practice using it, you can do a lot of like neat stuff with the type system. And one of those that I find particularly useful is with the integral types. You can do like you can specify the integer types being unsigned, which usually there's like no need to make that distinction, and functionally it won't change anything. But I find that is sort of very good inherent documentation, like writing unsigned int instead of just int immediately makes it very clear, or more clear, what the purpose of that variable is. Like it can't be negative, so it's likely like an index counter or something like that. And it also allows you to, or sorry, it allows the compiler to catch certain errors that you would make. Like if you're trying to get something from an array and you have like a negative index, for example, if you pass a negative index to a function that accepts an unsigned integer, it'll probably yell at you and say like it won't fail to compile because all it's going to do is copy the bits. But it'll probably say like, hey, this says unsigned, you gave a signed value, you probably messed up. So that's sort of going back to the whole point of like documentation is good. This is a very easy way to do some documentation without actually writing comments. We're also going to go ahead and include standard.io.h. I'm not exactly sure why I included that here, but it's useful. It just has like printf and stuff so we can debug to the console. And then we'll also include string, which has the STL, or sorry, the C++ specific string class, which we'll be doing a couple operations with. Okay, so now I'm going to do some type defs. So immediately right into some stuff that's like C++ specific here.
Is there any way you can make your font size bigger?
That is excellent point. Is that better?
Yeah, all good.
All right. So I'm taking these types from inttypes.h, these uint underscore t. I don't add the underscore t to my types, just I think it's dumb. Like, I don't know why you need to do that. But all of the standard library stuff does that. But the u specifies that it is unsigned, and then the number says how many bits it is. So a character, a char is 8, a short is 16, an int is 32, and a long is 64. So again, for sort of like inherent documentation, I find that using the most restrictive type that makes sense is often very good. And when we get to like reading and writing from files, it's very important that we count our bits correctly. So we'll just go ahead and specify these here just for convenience so that we don't have to write the number and then underscore t every time. Then I'm going to define some macros here. So these are pretty cool. Java doesn't have anything like this. I don't know if C# does, but it's like a preprocessor command. Basically, it says wherever I find this syntax in a file, where there's some text that I'll call t and some other text that I'll call x, I'm going to replace it with this format. Static cast is just an operator or a method defined somewhere in one of the files that we've included. And it just says like treat this variable x as whatever type t is, as long as it's safe. And that's very important, is that as long as it's safe, the compiler will try and yell at you if you like try to cast an int to a string. It'll say like, hey, that doesn't make any sense. And that's very useful. And in most cases, that will suffice. However, there are some cases where it's not necessary, but very convenient to cast stuff to types that the compiler won't like. And as programmers, we can tell that it's fine, that it's a safe conversion based on some preconditions of whatever method it's in that the compiler doesn't really understand. And this is called type punning, and it has some weird syntax. I think it's very cool. But what this does is it grabs a reference to x, whatever the variable x is. It casts that to a pointer of type t, and then dereferences that pointer. So essentially this takes whatever object variable x is of any type and converts it to whatever type t is. And I think I'll do a small paint illustration here. A good way to explain this would be like the whole casting versus punning thing. You could say, like, if I have, let's say, a u short, so a 16-bit unsigned integer value where each of these blocks is 8 bytes. So if I have like a u short x here, and I want to convert that to a short y with like short y equals cast, or sorry, yeah, cast to a short x. What that looks like in memory, I'll just copy this whole thing here, is it will take a memory slot of the same size, because a u short is just 16 bytes and a short, or sorry, 16 bits, and a short is also 16 bits. And it will perform some, no, the math folder was not in the setup. I just created that right now. I'll tab back to that in just a second, don't worry. So it'll perform some like conversion on that, because it knows, the compiler knows the difference between unsigned and signed values. And so it'll do like, say my u short x, I'll just throw a bunch of zeros in here. 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, that. So that's the value of 8, right, in my u short x. And in this case, there's no conversion necessary. It's just going to copy those directly in there. And then short y will contain the exact same bit pattern of 8 zeros, 4 zeros, 1, and then 3 zeros. But in the case where you're storing like a value, say, that has a 1 in this most significant bit place instead of a 0, when you convert that to a short, it sort of becomes garbage. Okay, I see someone has linked the very famous fast inverse square root algorithm there. That I would love to talk about. It's maybe I'll go into that in a bit. But yes, the fast inverse square root does use type punning, very famously. Yes, well spotted. And there's an excellent video about this as well that I'll link afterwards. I watched the other day that like explains what's actually happening, all the magic. So anyways, yeah, so when you have a u short x and it has this like 1 in the most significant bit place, and then you try to convert that to a signed value, remembering that, signed values, the most significant bit is the signed bit, saying whether or not something is negative or positive, that sort of becomes garbage, like this would be, I don't know, 6,000 something, or 60,000 something. But the maximum value for a short is like 32,700. And so the compiler will try to do some conversion there and like convert it into a valid value. But if instead we are doing type punning instead of type casting, and we say pun x as a short, the compiler will not perform any conversion on the types. It will simply copy the bits from u short x into short y, and you can now reference them as a short. And really, a better way to represent this, I think, would be to have one of these memory slots where you have, whatever value is in here. And then you have like u short x, which points to that more or less. And then short y, which now also points to that exact same memory address. And I think this is like a more technical way of explaining it correctly, just because if you look at what we're actually doing, we're using pointers, right? So we say, okay, I'll get the memory address of x. I'll say that's going to be type, like the type of and x is going to be u short star, right? But then I'll say, I don't want that. That's not a u short star. That's a short star. And then what do you get when you dereference a pointer? You get a value. And so it takes whatever value is there and stores it in y. So it's not really copying. It's just sort of using the exact same bits by a different name and a different type. And again, this is very dangerous. Not necessarily in the sense that like it'll crash your computer or anything, but you have to be careful when using this, just because you can take you could take an int and say, okay, this location memory, I'm going to read it as a string, and that could just go crazy, right? That's completely undefined behavior. So in general, we're going to be using casting, but punning is sometimes more convenient. Okay, that was a pretty long tangent, but I hope it was somewhat interesting. So now we're going to define this this namespace math, which is where we'll store all of our math stuff. It just helps keep everything like organized. If you're wondering what a namespace is, it's like, that example I gave earlier in the PowerPoint of like using the sign function, you would access that with standard sign, and you can see it's right here. So it's really just, I guess you could think about it if you're coming from like a Java perspective. It's like a namespace is like an object that only has public static fields, right? It's like something that's only there to access things by name. You'd never instantiate it for any reason. It's just sort of an organization thing. And of course that goes back to the like inherent documentation stuff. So we've got this namespace here. Let's just define some constants that are useful. And the way we do this in C++ is slightly different from C. We have, there is a const keyword. And one of the things I linked for you all to read in preparation for all this was an article. It's not really an article, but it's like a page about const correctness in C++. I'll find that and link that again. But that is something we're going to be trying to do as much as possible. And when we get into writing classes in a minute, I'll sort of explain why. But yeah, so read that if you haven't. But const is not the same as const expr. Const expr means constant expression, and it is a compile time constant, something that whenever you compile the program, the compiler knows what that value is. It's essentially just shorthand for you as the programmer to not have to copy paste this thing all the time and get the compiler to do that for you. Const is, as I said, is a bit different, but we're using const expr here instead of const because it is a compile time constant. The value of pi is not going to change depending on when we compile our program or any sort of other flags. So I'll just I have these values here written down so I can copy paste them. I'll put them in the chat just for convenience. Pi and e. I don't think we'll be making use of these like directly. Maybe we will, but first, like it's more for when we actually start creating games with our engine. Oh, which I don't think I actually said that, but the last sort of week, I think, like the last 2 workshops, we're going to have a sort of mini game jam right before the semester starts, where everyone will, like, you can group up if you want or just make something on your own. And you'll make something with our engine You can extend the engine if you want in whatever way, and then we'll all sort of go through them and present them one by one. Just because, what's the point of making an engine if you're not going to make a game? So yeah, these are more for that when you actually start doing like mathematical stuff in your game logic. So now we're going to do some more C++ syntax that I love, just for some simple methods. So we have abs here, which is classically absolute value. So if the value of this variable is less than 0, we're going to turn negative that. So if it's -1, we return 1. If it's 1, we just return 1. So this is similar, I think, to Java's generics system, where in Java you would have something like static, t abs, something like that. That would be the header. I may have done that in the wrong order, but in Java these are called generic types, and it's just a way of like writing a method in such a way that it can accept multiple different types of parameters. And obviously in this case that's good, because we might want to take the absolute value of an integer or an unsigned integer or a float or a double or something like that. And when we write it like this, in this templated way, two things happen that are good. The first is, obviously we don't have to rewrite this a bunch of times, where we do static int abs, int I, and then all the same stuff. So it saves us time, but also the compiler can perform certain optimizations depending on which template specialization is being used. So a template specialization is like, I guess the best way to explain this is a template is, well, it's a template. It's a blueprint for a function. And at compile time, the compiler will evaluate the type of what you've put in, which we've called T for shorthand. And first it'll check if that's valid. So it'll check if the operations performed on that variable of that type are valid. If not, it'll yell at you, which is very helpful. But if so, it will basically copy and paste the code of your method or your function into wherever you've used that template function, but as static float abs or static int abs. So it will do all that conversion for you, and that can lead to faster code and also code that's easier to write and easier to maintain. So we'll be making pretty extensive use of templates. The next thing we're going to do is, I always misspell this, type name A and type name B, and we will return a const A reference. Oh, I should talk about that. I'll talk about that in a minute. And this will return the minimum of A and B. So if A is less than B, we return A. Otherwise, we return B. Very simple. So yeah, the sort of const reference thing. The const I'll ignore for now, because again we'll talk about that when we get to const correctness. But the ampersand here might be confusing if you're sort of new to C++ or out of practice. But this is not the same thing as writing like in our previous example where we wrote and x, right? That means get me the memory address of x. I want a pointer to x. Instead, saying t and, some type and means give me this variable as a reference. And a reference is sort of a confusing concept. I think it really only exists in C++, where it's not a pointer, but it avoids copying whatever you're passing. So if I had just said, instead of a const A reference, if I just want an A, then whatever A is, if that's a string or if that's, some type of massive data structure with a million elements, when I pass it into this method, min is going to make a local copy of that, of A, right, of whatever type that is. And depending on what that is, that could be very expensive, especially if it's happening every frame that our game is running, right? So this is sort of a good introduction to like why thinking about efficiency is important and why C++ helps us do that, because it lets us be very specific about what stuff is and how it operates. But I would just like to make the distinction here that if I say min of x and y to a method with, it's going to give me a bunch of errors because I'm being stupid, but to a method that copies the a, and a method that, why don't I just do this properly actually? So I have min and min2. So min takes a value by copying it, and min2 takes a value by reference. And if I go into my main file here, I've already included these functions through my PCH, so I should have access to them with math double colon. So if I do min of 1 and 2 and min 2 of 1 and 2, you can see the syntax is the same. And this is one of the reasons I think references are very confusing at first, is because there is no obvious difference to the user of what is going on here, right? These are essentially the same function header. You can pass in exactly the same arguments, but the way the function receives those arguments is different. So just know that that is the distinction here. They are called exactly the same way, used exactly the same way, but to the caller, there's no difference. Okay, so we have min. We'll do max. At this point, we're more or less just gonna copy a bunch of stuff. Obviously, flip the sign there. We're gonna do a method called clamp here, which will use min and max to clamp some value to a range. So I'll have my value a, then I'll have the lowest value that I want and the highest value that I want. And I'll return, max of the minimum of my value and the highest value, and the maximum of that and my lowest value. So this is just some neat sort of simple logic. It looks confusing and magic-y at first, but it's very easy to decipher when you go back and write comments. So yeah, I guess before I go any further, can anyone tell me why for each variable I'm defining a separate type? Because really it would make just as much sense, right, to just have a type A here and then not have to worry about that other one B. Does anyone know why that is?
Could it be like if you want to compare like a float to a short or something like that?
Yeah, it's exactly that. It's very simple. The compiler, so I guess, let me redo that and I'll see what the compiler says. So if I have math min of 1 and 2 as a float, the compiler is going to yell at me because it says, okay, I've deduced that the first variable is an int, so I'm going to say a is type int. But oh no, the second variable, which is also a, is a float. And so it says there's a conflict there. But if I undo that and have two types there, that's totally fine. So it is ugly and seemingly like very verbose to write it this way. But I've found that just especially with like converting ints and floats and stuff, it's very good to be as explicit as possible, because those are just annoying bugs that the compiler is designed to fix for you, so, or catch for you. So why not take advantage of that? Okay, so now we're just going to do a bunch of boring stuff. Now that I've talked about all the template stuff, we're just going to wrap a bunch of functions from CMath, which we imported earlier. Just some common math functions here. We'll have square root, and I'll just copy and paste this a million times. We'll have sine, cosine, tangent, arcsine, arccosine, arctangent. I'll try and separate these out a bit visually. Even I'm getting lost. Okay, so we have sine, cosine, and tangent. And once again, the reason that we're doing this boring work is just because at some point in the future, if it becomes helpful for us to change the functionality of these or the way they work or the code they call, it will be much easier for us to change all of that. So for this ATAN method, I'm going to use standard ATAN 2, which is, I think, a bit better than just ATAN, because it actually like takes into account the direction of the vector that you give it, basically. Like normally it'll just return, ATAN would just return a value between 0 and 90 degrees, but ATAN 2 will be between 0 and 180. So that can just be a small thing for you to look into on your own, just at the documentation if you want. But it's not that important. And ATAN 2 does take the y value first, and then x value second. Okay, so now we're going to do a small bit of coding on our own, and there's some more interesting syntax coming up. So we have template, type name A. We're going to do a simple distance function, just the Pythagorean theorem that takes 2 points and returns the distance between them along a line. Make sure to change my types here, A, B, C, and D. Then we'll have a const A dx equals x1 minus x2. Here I will make the distinction between const and const expression. And then we'll return, we'll call our square root function with x squared and y squared, classic. Okay, so first of all, I guess the reason that I've marked these variables as const is inherent documentation. There's no reason, like they don't need to be. Logically, the program will compile and run just the exact same way if they're const or not. And in this case, of course, it's very trivial because it's a 3-line function. But if you've got some, longer function of considerable length and some real complexity, it's very, very nice to mark stuff that doesn't change as const, because it says to the reader, this is not something you have to worry about. Like, look at the value once, and that's the value. You don't have to track it. Can anyone tell me why these cannot be const expression? So the syntax highlighting is not yelling at me here, but if I go to build my project, oh, that worked. Well, I have to actually use it first. Let's say math. If I go to build my project, it doesn't like that too much. Can anyone tell me why? Okay, so the reason is because const expression is a compile time constant. And as you see here, we are taking these in as const references. So in this case, again, it's a bit trivial because I'm calling this function with integer literals, which are compile time constants. But if I were to do something a bit different, I don't know which file that's in, but if I were to get some number from the user types in some number, I store it in X, and then I calculate the length between, like the length of that line, basically. This, like, just conceptually doesn't make sense, right? Regardless of how these are being passed to the method, because X is dependent on user input, which happens at runtime, and therefore cannot logically be a compile time constant. So that's why these are const and not const expression. Const expressions are generally going to be defined in as static variables of various classes. or as you saw here, as just sort of static members of a namespace. Okay, so that's the distance function done. Now we're going to do, oh yeah, another thing that I like to do is have like my own sort of equality check. I'm going to do some ugly formatting here and just put this next constant definition so I don't have to keep scrolling. So I'll have a const express static float epsilon. And this is going to be like the maximum the maximum difference between two values for us to consider them the same value. I found this is useful when like comparing velocity vectors and position vectors. Like, say for example, you have some like ice material that your character is running on, and as they, if they stop pressing the key, the character will stop running, but they won't stop moving. They'll keep moving, but they'll be decelerating, and their sort of velocity will asymptotically approach zero. And it's going to take a very long time for it to actually reach zero, right? But long before that, will they stop moving on the screen? And so that's an example where using this epsilon value to say like, okay, if the velocity is less than 1 in 10,000, I'll say it's not moving. And you can change this if you want. We'll actually have a method here, set epsilon, so that can be set by the user. Oh, and that's not going to be const express actually. If we want it to be set by the user, it can't be a compile time constant. Why is that yelling at me? I think you're just being weird.
You spelled this wrong.
Did I? I did. Good catch. Epsilon. There it is. Okay, and then we're going to actually use this value to check if some other, numeric value is 0. Another thing here I guess I should talk about, a lot of these functions are like, they're written as templates, right? So they just have type name X, type name Y. But there are like inherently requirements placed on these variables, right? Like especially these where we're just calling some existing function. Like these standard math functions, I think they all take doubles. So what that means is that our type T, whatever that is, has to be convertible to a double in some way. The compiler has to know how to do that. And this is where C++ is different from Java. In Java, you'd say like this generic type T must extend some interface, implement some interface, in order for you to be able to pass it to this method. And that's actually nice. I think that's one of the things I like better about Java's type system, in quotes, compared to C++, is that you can be very explicit in that. And actually C++ is sort of catching up in that regard in the latest releases, C++ 20 or 23. They have this essentially the same system where you can be very explicit about what the types are that are required. But we're not going to be doing that. And that's another reason that I'm just sort of throwing this const t and on everything. Like obviously in these cases, if it's just a numeric value, there's no reason to pass around that specific value. We could just copy that value for essentially free. But I don't know. It doesn't really matter. Just if that was sort of confusing you, why I'm passing these integer values as references, there's no real reason behind it. It's just like that's how I decided to write this. You could just as easily write all of these, not all of them, but most of them as that, and you would have no performance hit. But it is important to note that in some cases you could that could hurt you, right? Like abs is defined in such a way that these like operations could make sense. you could overload these certain operators like the less than operator, evaluating the expression itself or the variable itself as a Boolean, the negation operator. You could theoretically do those and want to take the absolute value of some user-defined type. And in that case, passing it as a reference is just the safest way for the general case. Like something is probably going to be very small, so there's no reason to pass it as a reference, but it could be very big, so might as well. Okay, now we're just going to do, I'm just going to go ahead and copy this again. We'll just do some sort of quality of life functions. We'll convert a radian value or a degree value to radians using our pi variable, and a radian value to degrees by returning the inverse of that. Okay, now we have a bit more interesting syntax coming up here. I'll just get through it and explain it. All right, can anyone tell me what this does? Or what they think it does? Okay, so this is kind of a beast. We take in two template parameters here. One of them, as we've seen, is a type named t, so some variable type. The other is a uint. So we've actually specified a type here. It can't be some generic thing. It has to be an unsigned integer value that this template takes in. And what it says here is I'll take an array, a constant reference to an array of length n. And then I'm just going to return n. So essentially what we're doing here is we're tricking the compiler into giving us the length of an array that it knows, right? So when you write, if I have some int r of 5, and I call rlen on that, it will accept this, right? And it's not going to yell at me because that matches. If I instead change this to 50, and I try to build, oh, it works. Why does that work? Oh no, that does work. Sorry, because I have this. Let me erase this now. Just forget about the uint part right now. So you can specify this as a constant value, because remember that's essentially what the compiler does. Is it takes like code that you write and like replaces it with different code depending on the templates you've specified. So I could say, okay, I only want a reference to an array of length 5, and then I'm going to return the length of that array. It says in identifier not found, alter 5. Now it will yell at me because it says, okay, this function takes a const array reference of length 5, and you've given it one of 50, so it's not going to work. But we can generalize that with the uint in part, and as I said, sort of trick the compiler into giving us that number. Because obviously, in order to know if a parameter works, what's the word? It adheres to the requirements of this function, it's going to have to know the length. And then we say, okay, pass me an array. It's going to be of length n. I'm not going to tell you the length, but you're going to know it. Store that length as a variable called n, and then just return n. So this is a neat little trick. The one downside, though, is that it only works on compile time arrays. Another way to say that, I think that is not entirely true, but for our purposes will be true, is a stack allocated array. I guess, first of all, is everyone familiar with the difference between the stack and the heap? I feel like that was probably covered in CS 2337 or whatever. No? Okay. I'll go over that just a bit here. So the stack is like where your methods and stuff execute. So we have this method called main. I'll write one for our program here. So we have main, and then that calls this method rlen. So rlen will be another frame on the stack. And that has its own local variables, its own sort of scope. And then when rlen is done, when it returns, the value is sent back to name, and that frame is popped off the stack. So that's all good, but in order for the, computer, the CPU to know how to call a method, it's going to have to allocate a frame for that method to store all of its local state, all of its local variables. And if you have like an integer, like let's say I was going to do, I'll go back to my user input example here. If I get some number from the user and I say, okay, now I'll define an integer array of that length. Well, I should write that the other way. That's not going to work, right? Because now when the CPU sees main, it's going to say, okay, so I need to allocate space in order to get the size of this array, but because I need to get the size of the array, I don't know how much space to allocate. So that's just clearly a contradiction. It won't work. And so instead we have to do this more Java-like syntax of the new int and then x. And this allocates it on the heap. So the heap is like this sort of nebulous area in memory that is where anything that is of a non-compile time constant size is allocated. And again, there are ways around this, but I'm not going to touch on those. So that's the reason that this only works on stack allocated arrays, because the size of those arrays is known at compile time. And when is this template specialization created that, has the correct value of in that spot and has the correct value of the type of the array? That happens at compile time. So all of this has to happen at compile time. If you define one on the heap, it's going to say, it's not going to work. It says no instance of function matches the argument list. You're passing it an int pointer. It doesn't want a pointer. It wants an array reference. So we'll probably talk more about the stack and the heap. I think those are very important concepts. Just like knowing the difference between the two, how the stack is meant for stuff that is of a definite size at compile time. And it's also where all the methods and stuff happens, all the method calls. And a heap is just stuff of variable size. For example, in Java and C#, which is another sort of managed language, the garbage collection system handles all of your objects and everything. Like when you write, object O equals new object, whatever, in Java, that new essentially does the same thing it does in C++. It says, okay, allocate me space for this thing on the heap. It's just all managed there. And we'll get more into that. But again, that's simple syntax that you should really know about C++ if you've had to study it. So then we just have rsize here, which is essentially a copy and paste of rlen, just we multiply by size of t. So this will give you the size in bytes of a compile time stack allocated array. And you may be wondering, like, what's the point of having these methods if it's a compile time constant? Like, if I'm the programmer and I'm specifying the size of this array, why do I need a method to tell me the size of the array? It's just simplicity. Like if you have this and then you want to like use the length of this array in multiple places, you could write 5 everywhere, but then, what if you change this to 50? You'll have to go back and change all of those 5s to 50. Whereas instead, you could just say rsize of the array and then use that. And it'll get the correct value for you each time. Okay, last few functions here. We're going to finally use that string stuff we included. We'll take a standard string. Very important to take this in by reference because strings can get very large and you don't want to have to copy all of those characters. But also in this case, we're not taking it as a const reference because this is too lower. We are taking a reference to a string and modifying it. So let me just write the method and then I'll show you the distinction there.
I just had a quick question. Sorry for
No, go ahead.
interrupting. So when I was doing the set epsilon method, so I'm getting a cannot assign to variable epsilon with const to qualified type.
Did you say const expression static float epsilon?
I did say const expression.
Yeah, I did that at first too. That's an easy mistake to make, but yeah, if you want to be able to change that, which you might not. It doesn't really matter, but obviously if you're going to change it, it can't be constant.
Oh, okay, yeah, missed that.
All right, so let's. Oh yeah.
I want to ask, are you gonna leave the source code?
Yes. So I think the way I'll do this is I might have some GitHub repository that I'll set up, or maybe I'll just hand out a zip file at the start of each meeting. But like at the start of each meeting, you will have access to all the code I've written up to that point. So if you have to miss a meeting, you can just sort of jump in at any time and get the latest code without having to write all of it yourself.
Okay. I wanted to have it after this meeting, not before the next one.
Okay.
Yeah, to look at.
Yeah. Okay. So I can give that to you. The idea though is that like, and again, you can do this in multiple ways. But the idea, what I was imagining is that like you guys will be copying the code along with me, as I think some people are. That just helps me learn. But if you prefer to sit and just sort of watch these, that's perfectly fine too. But also I'll be posting a recording of this. So if you want the source code, like you can go back and watch that and copy it yourself.
Oh, okay. I'll watch the
As you're writing
video.
comments. Yeah.
You were just typing too fast and I lost track.
Okay. Yeah. I'll try and slow down in the future. Sorry about that. But yeah, I can get you the source code right after this because this stuff, like, there's not really a need for you to copy it yourself. It's very simple. And I've sort of explained all of the, the small interesting points about it.
Okay, thank you.
But in future with the more complicated stuff, you can like go back and watch the video and copy it down yourself as you're writing comments. I think that could be good. Okay, so let's see what this toLower method does, how it works. So I'll have this, and then I'll call my math toLower on S, and then I will print out s.cstring. So this method just gives you like a char pointer to the string that this object encapsulates, because that's what printf expects is a char pointer. So if I run this right now, obviously I'll see ASFD because this was all lowercase to begin with. But if I go to uppercase here, I should see the same thing, all lowercase. And the reason for that is that I've passed S as a reference. If I were instead to pass S by value, that is to say to copy it, and then run, you can see it doesn't actually change it. Because what I've done here is I've taken this variable, S, I've copied it over here, and I'm changing the value of that copy. So when I print out the original, it hasn't changed. So that's why we do reference there. An important thing to see is if I write const reference here, as I've been doing for everything else, and I will make this mistake many times undoubtedly just because you get in the habit of writing const whatever and, the compiler will yell at you. It'll say, hey, this reference or this method or whatever operator you're calling on this object changes the object, but it's const, so you can't do that. And that's another reason why I'm really going to push for const correctness for all of our code, because we want the compiler to catch as many of these stupid little errors as possible. So that's the toLower method. Then another sort of similar method is equals ignore case. We'll just take two constant strings in this case, constant string references, and we'll just see if they match without caring about capitals and stuff. And this is useful. I think we'll be using it for like file paths and stuff where depending on what you type, like you know how Windows file paths, like you can use capitals or whatever. It doesn't matter. It looks at them in a case agnostic way. So that's how we'll compare them as well. And for this one, what we could do is we could say like, okay, I'll take in copies of these strings, and then I'll do like standard string A lower equals 2 lower on A and B lower, blah, 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 and then return if those two equal. And that wouldn't be too bad, but it still has this initial copy. It copies the parameters. It makes a local copy of A and B, which is not what you want. And while that would be like cleaner and more satisfying to use code that we've already written, it's performance-wise, it'll be a little bit better if we just write this ourselves. So if the sizes aren't equal, obviously the strings aren't going to be equal. So we'll just return false. And then we'll loop through each character. We could do a.length or b.length. It doesn't matter there because they're the same. Oh, by the way, for strings in C for this class, size and length return the same thing. So I'll just use size there to be consistent. And then we have this nice method toLower, which gives you the lowercase of a single character. And if any lowercase characters are not equal between the two strings, then they are not equal agnostic of case. Otherwise, we've gone through the whole string and they're all equal, so return true. So that's some very simple logic, but could still be useful to comment that. And you can see now, just for purpose of proving this out, we can do equals ignore case on, actually, yeah, I'll do this first. So I'll have string A as that, and then B be the lowercase version of that. And then we'll see if A and B are equal. Ignoring case. And this should print out 1. Yes, it does. Another thing we could do, which is kind of cool, is just write the string literals there, and that'll do the exact same thing. And the reason for this is that, which we'll get into a bit more when we start creating our own types, but the compiler sees this and it says, okay, so what I have here is a const char pointer. That's what this string literal is. And what this method takes is a const string reference. So then it looks at the type string and it says, okay, I see that there's a constructor for this type that takes a const char pointer. And it'll do that conversion for you. You don't actually have to predefine them. And this is what's so cool about C++, is the whole type system is just very, very like extensible. I've watched several talks and I can probably find them and link them. The guy who like first created C++, he said that was like one of his initial goals, is that the type system is completely user extendable. And we'll see that a bit more next time when we get into like some basic operator overloading stuff, which is very, very cool as well. But yeah, that's the reason you can just write it like this, even though these are not strings. And I'm making this distinction because I'm assuming that if a lot of you aren't familiar with C++, you're at least familiar with Java. And in Java, this syntax literally returns a string object. String has this sort of pseudo-integral like status where it is a class, but it's also like you can create it with the double quotes. But in C++, this is a const char pointer, and it is the compiler is converting it to a standard string through the constructor. So yeah, that's about 5:30. That's all we had time for today. On Wednesday, we're done with all this boring stuff. We're going to start doing a bit more of mathy stuff. We'll get through the 2 classes we're going to write for our math library. And then maybe have some time for graphics. I don't think we'll get into graphics programming, but I might have time to go over like the that thing I said, like just explaining like what a GPU is, what's the whole pipeline for graphics, how do pixels end up on your screen, all of that, depending on how fast we go. But yeah, I hope you guys enjoyed, and I will see you on Wednesday. Just real quick before you go, though, obviously someone already said that I was typing a bit too fast, which is great. I'll try and keep that a bit slower. And I know it must just be so confusing when I'm scrolling around like this. That's why initially I had my text a lot smaller so that I could just, like, you could see more at once, but I can see how that's frustrating as well. So I'll have to try and find a happy medium there. But how are you guys feeling about like the pace of this in general? Like, was I covering stuff that you mostly already knew, or do you not know it and it was like I was explaining too fast or too slowly? Any feedback on that?
I think
Maybe you could have.
pretty good.
Pretty good.
Honestly.
All right.
Like most workshops that I usually attend, it's just an overload of information, and it's just like going over stuff. But you did a good job like explaining what each thing does. I
All
do
right.
agree that you were typing too fast.
Okay.
That's my feedback.
Good. Thank you.
Yeah, more or less what everyone else has been saying. I think the rate of pace is, it's like it's a decent medium, so it's not like too fast, it's not too slow, because like, yeah, you probably figured out why it's good.
Mm-hmm. Right.
I
Okay.
like it. I plan on rewatching the video though, but I like the
Okay.
pace.
All right. Cool. Thanks. Yeah. So that's it for today. I had, before I forget, there was one person who had an issue with OpenGL setup. I'm not sure if they're still here. They may have left. And Eduardo, you pointed out the fast inverse square root thing. I'll find the YouTube video for that and link that. And also the article on const correctness, which if you have not read already, I really want you to read by next time, because we are going to start using that. And the syntax, it's like simple but very confusing. Like the differences that are made based on where you put the const, and we're going to be using it very liberally. So please read this article on const correctness. But yeah, other than that, I had fun. Hopefully you did too, and I'm looking forward to seeing you at 4 p.m. this Wednesday. Thanks, everyone.